and we will now continue working with the road network data. Let's again start, well, I will maybe explain a bit and then we'll start hands-on quite soon. Close some of these windows. Great. So network analysis is a topic in, well, geospatial data analysis that is often very useful, for example, in urban contexts. So the main problem is to find the shortest path in a network. So this is, as such, it's not a geographic problem, but then if we analyze geographically referenced networks, then it becomes kind of a geographical issue, but it's a common problem in computer science in general. Some of you might be familiar with Dijkstra's algorithm, which is one of the many available algorithms for solving the problem of finding the shortest path in a network of edges and nodes from one point to the other. I won't explain Dijkstra algorithm in detail. I think you can even find the Python code from NetworkX documentation on how it's implemented. So it kind of goes through from one origin node in the network. It finds the shortest path to all of the other nodes. And then based on this, we can answer our questions. Maybe a nicer motivation would be, maybe I can show this. This is not, well, not purely a Python example, but an example of shortest paths. So a tool developed by Joose Helle and others in the HOPE project, where the idea is that we can, let's see, geocode some locations, and then let's say Portania. So from the Kumpula campus to the city center campus, let's find the quiet path. So it's of course very common if you're when you used to come to the campus, or if you're going somewhere, you take a routing application, and based on some weights in the network, for example, speed limits or something else, it will calculate you the shortest path in terms of travel time or distance. And in this application, the idea is that then the weights in the network are based on noise levels, so decibels, and then it will suggest you then the kind of shortest path is maybe not the nicest path in a way. So shortest then in terms of some other measures might be the one that then gets a kind of lower scores in terms of noise level. So this is quite a cool example that was released now. It's a prototype, but also available as a web application from the Helsinki region. So we won't be going quite this far, but repeating the basic analysis of finding shortest path from A to B in a network, and particularly street network fetched from OpenStreetMap. Let's go to the other notebook over at CSC to get started. And here we will primarily now start using this NetworkX Python package. And you can then indeed read more details of the algorithms behind from this documentation. Was there something else worth mentioning? Yeah, so when we soon will again fetch the street network, it's important to think about what are we routing. So in this Green Paths app, the routing can be done for pedestrians and bicycles. In OpenStreetMap, we have information about drivable networks, walkable networks, bikeable networks in a way. So I would say that now that we're analyzing Kamppi, it would be most interesting to analyze the walkability of the of the city center, but it might be that for technical reasons, again, oops. Sorry, can you still see my screen? I accidentally opened a pop-up. It's a day of technical stupidities. Yes, great. Okay, so let's just move on. There's quite a lot of packages that we're importing. OSMNX we will use for fetching the data, NetworkX for the network analysis, GeoPandas for manipulating data, Matplotlib for plotting, Pandas probably later on for some basic tabular data manipulation, and we are furthermore importing PyPro-CRS to do a bit of management of the coordinate reference systems. So as you can see, there's tools that we have learned along the way that will pop up during this tutorial, but the main tool is indeed this NetworkX. Yes. Yeah, and yeah, still about NetworkX. So it's basically for doing these shortest path analysis, and then furthermore for studying the structure and dynamics of the street network or complex networks in general. So I highly recommend watching this YouTube video where Henrik is interviewing Geoff Boying about some additional analysis you can do with these types of data to get some more inspiration. So let's get going. We have the same place name there that we used already earlier. And we will repeat what we did. But now OX. Using this graph from place, from our place name, now we will all define what type of network we are analyzing. And I want to be bold and take, well, I will take the drive mode. But if you want, and if you get the response rather quickly, you can also specify walk as the network type parameter, because as mentioned, I think that would be the more kind of interesting thing to analyze in Kamppi. So you might then get a bit different results than I do, but all the processing steps should work for also the walkable network. Let's plot it again. So now that I only have the kind of drivable ways, the network is a bit more reduced compared to what I had in the first part of the lesson. I will pop up this participant list, and in case you have some problems, put the red X, otherwise I will proceed. So this went now rather quickly through, and indeed do try the walkable network using the walk param attribute if you like. Yep. So then we continue to investigate the network object a bit more closely. So I've been mentioning that there are these edges and nodes, the lines, and then these junctions in the data. And previously we used this graph to geodata frames function to fetch both the nodes and edges. But then there are these additional parameters where we can flag that, okay, we don't want the nodes, we only want the edges. Well, let's do that just to exemplify how you can then modify this, how this function works. So let's have a look. We now have the drivable network. There are the IDs, one way, the same parameters we saw before. And then we can also check the CRS. So this data is in 4326, so VGS 84, so in this kind of geodetic coordinate reference system. And quite soon, as we will be analyzing distances and so on, so it will be purposeful to project the data to a projected metric coordinate system. And once more, we can see the structure. These are now the line objects we have. and there's a bit of more explanation on the attributes. So as said, most of these come from OpenStreetMap, and probably these links work and will take you to OpenStreetMap wiki. So the highway tag is quite important. Speed limits, we could use those as our cost value. But then these two last ones are then come from the Network X tool, which are then linked to the kind of properties of the edges. So which is the node ID where one edge starts and where does it end? Just for you to understand the attributes we get from there. So we can have a bit closer look at the highway column, which is one of the most important ones. So edges, highway column, and then there's this value counts. Maybe I'll print this first. So always, if you have categorical data, some discrete classes or attributes or whatever, so then there's this value counts function, which is quite handy, which then will summarize data from one pandas series and give the count per category. We have used, or at least some of you have used this before in some of the exercises, but just to highlight it here as a pandas trick. So most of the streets in Kamppi are residential, quite logically, but then there's also these higher classes where trucks are going, and then there's some unclassified roads. If then we would be mapping, let's say, some unmapped territory in Tanzania that we have been doing in the humanitarian mapathons, me as a Finnish person from Finland, I will mostly tag the streets as unclassified because I don't know the local context of the street hierarchy. But of course, nice if there is this more detailed information of the roads. So as mentioned, we want to project the data, and this can be done. Of course, we could project the data in GeoPandas, but we still want to work with the routable network that has the nodes and edges and all the topology in place. So let's project the data using this OSMNX project graph method. So by default, this will project the graph to the universal transverse Mercator in the local, according to the local context, and could be also then used to project to other CRS as well. But we are happy with the default one. I'll show the details of that in a bit. So let's call it graph project. Just to remember that this is now the projected one, and then OSMNX. Oops. Project graph. There we go. And now we have, when we do this, so this is still a graph object. If you don't believe me, I can prove it. Oops. So I still have this graph object, but it's now projected. And from there, once more, I can then get these nodes and edges. Now we'll get both of them using this graph to geodata frames. And there's GDFS because we get multiple ones. Okay, so now we have still the projected graph, and we can take the nodes and edges for further inspection and through OSMNX, we now have the data in the UTM zone 35 Cartesian projection, so a projected system. Let's see where this link leads us to. So if you want the basic definition of the UTM projection and different zones, you can read the best source ever, which is Wikipedia. But indeed, this zone 34 on the northern hemisphere is the one that matches with the Finnish region, and it has a specific EPSG code that we can check using this readily written code cell. Let's still also then, if we have this edges data frame, just to have a look at the data. Data a bit more closely, but maybe I still want to open this one. Yeah, so here is then the EPSG description of this particular UTM projection, in which then we can actually analyze distances on a plane. So this next section, then I have left all the codes in there because it's quite detailed and you just need to know the syntax. So let's just run the codes and discuss a bit what these statistics mean. These are not central to this week's exercise, so I'll go this through a bit quickly. But if these kind of network metrics and network statistics are something that you are excited about, so then feel free to apply these skills, for example, in your final assignment. So we have now the projected graph, and we can then, using OSMNX, that is the tool for actually analyzing then these networks, we can generate some basic statistics. So descriptive metrics, information about the topology, and so on. So there's a bit more detail of all the available statistics here in the documentation. But if we call OX basic statistics, give the graph, and now that we have the projected layer, we operate in the Euclidean, or no, this is actually now not yet about that. Yep, but there is a specific measure that will then use this kind of Euclidean, so shortest path plane straight line distances for calculating that particular one. I'm not so familiar with that one, but let's just see. So there's things related to node density, edge length. So these are kind of just like raw statistics, but if you then start thinking about them in terms of urban structure, you can, and if you will look this look up work by Boeing, so you can then start seeing how these could be, for example, used to comparing different urban regions, understanding the urban structure better in terms of the street network and its structure. Okay, then for some other statistics, we need to kind of define the extent of the street network. So we have calculated this convex hull before. Something like this you might need to do in the exercise, so maybe pay attention. So I'm passing all of the edges, making a union out of those, and then for that kind of multi-line object, creating the convex hull, which is then outlines the extent of those line objects. And then with that, first calculating the area, and then for some more further basic density calculations, then this area information is needed. And then we're doing some sort of Panda series tricks to get the output that we get from this extended statistics into a nicer format. Just to summarize what's happening in here. So here's a bit more comprehensive list of of statistics describing the structure of the street network. All right, so sorry for skipping that a bit, but I think the most important is to focus on the main topic, which is the shortest path analysis in this network. So let's walk through this in detail, and that's now the main topic for the rest of the lesson. So here, as you remember, we are operating in the Kamppi area. Most of the Finnish students are probably familiar with that area. There's, for example, Tennispalatsi and the Kamppi shopping center in there, and the polygon we had extended even to, I think, was it until Boulevardi or something? So in order to demonstrate the shortest path analysis, we need some origin point and some destination point. So two locations in Kamppi. And there's different ways to define these, but the basic goal for us is to have one shapely point for the origin and one shapely point for the destination, and then we link those points to nodes in the network, and then the routing will actually happen between the nodes in the network then. And for this, I have proposed two locations. So there's this Maria 1 kind of old hospital area that is currently this startup hub that's located on the west side of the area. And then other option would be to analyze routes from Tennispalatsi, but I was just testing it today, and this won't actually work for the drivable network. So if you did as I did and had this drivable network as the starting point, so let's take this Maria 101 Helsinki as our origin point. So of course we could manually define the coordinates latitude, longitude, and create a shapely point out of that. But now that we just learned how to fetch data from OpenStreetMap, let's use those skills and kind of automatically fetch the technical information of this, the location of this Maria 1 building. You'll soon see on the map where it's located if you're not familiar with that one. So let's start by defining our origin point. We have the place, and then as we learned before the break, we have this OX geocode to geodata frame. Place. Need to run that cell, of course. And now, using this logic, I will get a polygon as output. So this is the same what we did for geocoding the Kamppi area. Of course, I could have then, for example, fetched the restaurants and then fetched based on the restaurant name one of the restaurants and getting that point. I'm sure you all would be able to do that. Using this approach, now that we have a geocodable place which is related to some kind of footprint, so the building footprint on OpenStreetMap, that is the one that we get from here. And then as an approximation for this location, I could then use I will propose that we use the centroid of this polygon. You could make it more advanced and use the entrance of this place or whatever else, but we will here use the center point of this polygon object. But for the routing analysis, we will want to have that geometry also in the same coordinate reference system. So just to be sure, let's reproject the data. I'm not actually sure if this is super crucial step, but let's go. So we have this geocoded place to CRS. And then on the fly, we know we have this now, we have projected the graph. So we have this edges geodata frame that should have the correct definition. And if you would run it like that, you can see that you might get some error because the edges actually have the coordinate definition in this old proy4 string format. And if I do this in place, I will just replace the object that I have in there. Just to make it clear, I will print out this edges proy. Well, yeah, actually, I think it will work without CRS object then. Never mind. These projection things have changed quite a lot in the couple of years. So let's verify geocoded place. Now we have our geocoded place in the UTM zone 35 projection. And then we can get the centroid using our skills. There it is. This is actually a GeoPandas geoseries, and we want the actual shapely point. So in these kinds of cases, we want to get the values of that series and then the first value of that series, which will then return us the actual point. Okay, so I want to store this one as our origin. I'll quickly recap, and if this went super too quickly, maybe have a look at the website, or then you can also shout out that I'm going too fast. But basically, we defined a place, we geocoded it, happened to get a polygon because that's what this tool gives us. Getting then the reprojecting it, getting the centroid of the polygon, and then now we have a shapely point in the correct CRS that we can then have as our origin point for the origin destination analysis. So we have this Maria 01 that's located in the Kamppi region. So then we would need a destination point. So if you leave Maria, where would you want to go? Probably the railway station, but for simplicity, we will now, as we have a restricted network only from Kamppi, we will specify one existing node in our road network as the destination. And as Maria is located kind of on the west or southwest side, let's have the destination be on the easternmost side of Kamppi. So this is a bit of an arbitrary example, but let's work it through. Continue. So we have these nodes stored in this geodata frame. So one node per each junction or other breakpoint in the network. And now, as we defined it, we want to know what is the easternmost point of these nodes. Maybe still, just to make it super clear, I'll scroll up and show this one. So Maria is actually located somewhere in here, or at least the driving route goes. Is it then Mekeliininkatu? And then the easternmost point would be this one in here. So we want to route from here to there, and then maybe continuing to the east. Scrolling back down. Where was I? There we go. So we have this y and x coordinates. So easternmost equals to maximum x. So we can use that information to define our node. So let's just get the maximum x into a variable to reduce complexity in the code that comes afterwards. So from this column, give me the max value. As simple as that. If you want, you can print out that value. So this is one x coordinate in this UTM projection. And then I want the whole row of data where for this maximum x value. So using our Panda skills, maybe I'll first show what it does. So nodes, Troji, using the lock, we have a condition, and then yeah, actually I want the geometries of that that node that way. So I want the contents of the geometry column only. And then my condition is that in my nodes, based on this X column, where all those rows, so there will be only one, where this X column equals the maximum of all X values. It's a bit far-fetched approach, but this is one way of kind of fetching the values out. So this will return the row of data, or one actually geoseries of this node. And then if I take values, so again, I want to only get the now it tries to print it out. But if I then take the actual values from that series, so the first value, as there was only one value, and print that out. So then I have a point object for my destination. So here the key is, now we're kind of generating data for this arbitrary example in Kamppi. We have one destination location. We managed to get the point, Shapely point for that. Then we decide that go to the east as far as possible, and we found the easternmost point as a Shapely object from our network. So these 2 points could be then whatever your home location, and then the shopping center, if you would be doing the analysis from the scratch that we did in, was it exercise 3? So two points in the coordinate reference system of the network. But now we still need to link these 2 points to the network, because as mentioned, the routing or the Dijkstra algorithm in practice will operate on the nodes and edges in the network. And now it happens that our destination point is actually on the network, it's on the node, because that's how we defined it. But our source point, there's no guarantee. So it might be that the network goes here, and then Maria is located there, so that they don't intersect. But using the tools we have, we can then actually find for a spatial location, whatever location, we can find the nearest node in the network, and then from that node we start the actual shortest path routing algorithm. So for example, if thinking conceptually in the travel time matrix, there is the routing done, for example, then in the drivable network, but then the analysis also includes walking from home to the kind of network node. So, and that of course adds complexity and time to the analysis. So if you need to walk from the parking lot to the office building, that's then sums up to the total kind of door-to-door travel time. Anyhow, let's find the nearest nodes in the network for these points. And in OSMNX, there is this get nearest node function. I'll again quickly flash this. Well, was the nearest? Yes. Get nearest node function, and basically does what it tells. So find the nearest node in the network, so in the graph, to a point. And it will actually here the important thing to notice again is this latitude and longitude point. So last week I shared this latitudes and attitudes YouTube video. You can check that to remember that latitude changes in north-south direction, that longitude changes this way. So latitude is Y, longitude is X, but our Shapely points have it the other way around. in these, when in Finland, this coordinates that starts with 6 is the y coordinate in a way, and this is the x coordinate. So we need to flip those around when passing shapely points to the then OSMNX nearest node tool. Great. So get origin x and y coordinates from these origin and destination points, which are shapely points. So we can do origin y and origin x. And then same here, destination. And we will pass this, we will create 2 tuples, coordinate tuples that have the coordinates in the right order. So if I now print out, for example, this target xy, so you can see that it now has this, the one that starts with 6 is first, so the y coordinate, and then the x coordinate flipped from this order that in which shapely represents the points. So just good to pay attention to this. And if uncertain, often the documentation should specify what is the order of passing the parameters. Okay, so now we have these coordinate tuples in the format required by the nearest node function. So for the origin, we can do OSMNX get nearest node. Then we pass the graph. So the projected graph, and then this coordinate tuple. Yes, so here the method, we are using the Euclidean method, so shortest path in a kind of flat world. If we would be operating on a surface of the Earth, actually using these tools, you could also calculate shortest paths using this kind of Haversine algorithm, which is then specified in here. Yep. So if we would have decimal, it would be possible to do this with decimal degrees, but it's, as we have such a restricted area, it's more meaningful to have the units in meters. Yep. So that's the Euclidean method. And what this returns, still going back to the documentation. So it is the ID of the nearest. So for that point in that network, the ID of the node. I just write it there to print the result out. So this now here refers to some of the, we had the data somewhere in here. So one of these nodes does have this ID, and this node is the nearest node in the network to our Maria startup hub in Helsinki. Same for the target. I'll just copy paste and modify target xy. Method is the same, and then let's print that out as well. And here actually this is a bit useless because we arrive back to the same node that we started off with when defining the easternmost node. Where was it? Anyway, oops. So, well, anyway, that node ID we get, it is related to this. I can actually, now that I started to talk about it, demonstrate it. So if I would then just do this, locate all those rows with this maximum x, so the easternmost node. So the node ID is exactly the same that we then get in here. But in case you would have some other type of input data, then you need to fetch the node ID, both for the source and for the destination. Good, good, good. Then we have the node IDs. Before we can do the actual routing, we need to fetch information of that node from, we actually don't need, but we're just doing this. Well, let's see, what good is this? So we have the node ID in there, and we have the nodes in the geodata frame. So we can, at least for additional information, again, using lock, we have these node IDs as the index labels. So I can pass this node ID in there, same as for here. I think this step is not strictly necessary, but just to know how then to access all the information. ID. So then, for example, now this origin node, this is a Panda series with information for that one row. And if you run this cell, everything is ready. I pass for the geodata frame constructor these two Panda series, define the geometry column and the CRS. So then we can create the geodata frame out of those origin and destination nodes. If you then, for example, want to plot those points afterwards for visualization purposes. Anyhow, so I hope you were able to follow at least a bit. In short, this was a complicated way to get 2 points out of the graph, for then finally to do the actual routing from one point to the other point. So from Maria to this easternmost point. So then we introduce yet another function, this time from network X, and this is now the kind of the thing. Kakku is here, so the cake. We will pass the graph, source node, target node, and if we would want, we could also pass the weights. But here we will basically do the, let's see how we are actually going to do the weighing. So we will be weighing the data based on the length of the edges. So the longer the trip, then the longer the distance. But we could also have them, for example, time that it takes to travel through one edge calculated, then pre-processed before the routing analysis. Anyhow, so let's use this tool. I wonder if there's still something I want to mention. So there are, just to note that then there are some other variations of shortest path methods available in Network X, but I won't go into detail to those because I haven't personally used them. But if you have a specified shortest path case, you might want to have a look at additional documentation. So routing from Maria to east, we will now use NX, Network X, that we imported at the beginning, shortest path. And then passing the parameters. So we have the graph in the projected form. Then source is our origin node ID. So basically here it says starting node for the path, but basically what we need to pass is the node ID in this graph object. And then target is target node ID, and then weight equals to length. Length of the edge will be the weight of going from one node to the other. And before running, this might take a bit, maybe you already ran it, but I'll print the results in the same, and then I have syntax error. Yes, well, it doesn't take that long. I'll just check if there's any. Yes, so it went through, but we still need to further process it to get kind of get some sense out of it. So what this function returns is a list or dictionary. This is not super informative, but it promises to compute the shortest path in the graph. So what we have in here is actually a list of nodes. So the kind of route from Maria node to this destination node, and the list of nodes through which we need to pass in order to reach the destination, and the shortest combination in this specific order in that specific network. All right. So we can plot this first. Good to see it on a map. And now again, using OSMNX tools, if we have the graph object and the list of nodes for the route, we can use this plot graph route function. And what we get in here, I have now this routable car network. And then you can see that, well, Maria was located somewhere in here. This was the closest node. It goes on the right lane, has to go from here, then straight road and off to the easternmost point and beyond. If you took the walkable route, you might have a bit different looking network. I think it's still not able to pass from here. There might be a possibility, but it goes from somewhere in here, from Maria to the east. And then same thing for Tennispalatsi, which is somewhere in here. Okay, I hope that went well. Maybe at this point, if you're having some trouble or you're stuck, you can let me know. We have time to discuss this. But this is, of course, this is still very simple, but it's at the same time, I hope you understand the basic principle if you're not super familiar with shortest path algorithms. So we operate in the nodes and edges. We could have weights for the edges and so on. And then we need the actual locations then to implement the analysis. We're almost there. Let's just then see. Now we only visualize the results, and it's in this kind of not so GIS friendly format, let's say, only a list of nodes. So let's process it a bit further to get the data, for example, saved onto the disk. So now again, we can fetch, we have these nodes. So the geodata frame that contains our nodes as points. And if we use the lock, you remember that the nodes data frame has the node ID in the index. So you can pass this list of indices, and then I print out the result. So this now contains all the information for all the nodes that belong to our shortest path as a geodata frame. So point objects as Shapely. Then we can also create, so based on these points, we should be able to then create a line string. So what happened in here is that OSMNX dealt with in the background of creating this nice line, but we don't have it anywhere. So the line representing the route, we need to create it ourselves. So we have all of the points. For this, we are importing a couple of new tools from Shapely, and using this line string constructor, we can then, well, I'll just do it as we're doing it in the lesson. There might be a couple of different approaches for this, but line string constructor takes a list of shapely points as input. So we can list from the previous data frame the geometry column values. So this will be all the shapely points, and this will create a Python list out of it, passing it to the line string constructor. Let's just quickly check. Something like this. So geometry column values as a list. I think there's this to-list function in Pandas that might be a bit more pretty to use, but whatever works. And then finally, I think the rest of the code cells are written in there because I was anticipating that energy levels might be going down at this point. But what we are doing in here is that we are creating then, so this is just a shapely line string in here. We create a geodata frame out of it. So passing the data, defining parameters for the geodata frame, and then populating OSM ID column with information from the root nodes. So adding information of the nodes or the OSM attributes, and then furthermore, now that we have the data in a projected system, we can calculate the length. So we have that information in our geodata frame. And let's see what all of this produces. So basically this part here, add list of OSM IDs. So this is kind of the source data based on which we created the line string. So we don't lose the information we got from network X. We have now stored it in our geodata frame. This might cause problems when saving to specific data types, but let's see. Let's see what happens soon. Okay, so now we have made the shortest path routing, saved our root nodes, created a line string based on those, and just to have some data to visualize it with, I'm again apparently fetching the buildings. Let's see how fast that goes now. And then finally, you can plot your own map and start modifying that. It didn't take too long. So this is now created with GeoPandas, building polygons to provide some context. Then we're plotting the edges and nodes from our network, and then the actual route here now with a specific line style to highlight the route for then to be saved as a PNG file or whatever. Of course, we can also save this the output directly from OSMNX plot graph function to a file as well. Great. So what else? I guess the rest of these code cells are preparing the data to be saved into a file. So as I mentioned, well, if saving data to shape files, we of course have some nice alternatives, but good to know that all data formats don't support all types of columns, so, such as lists. So we can then, for example, like this, exclude some of the lists that contain invalid data types. And then finally, this should then save it to a file, but we need to create. If you want to save the data to disk, you don't actually have to do that, but just to give you the syntax of how to do it, then you can finally have these streets saved into a GeoPackage shapefile, whatever, by modifying the last last piece of code in there. Okay, so that wraps up the network analysis lesson. As mentioned, this is kind of the basics of basics, but I'm sure there's enough work for you to do in the exercise 6 then to really learn these methods. And as I mentioned in Slack to the Helsinki students, so I haven't yet activated this link. I hope it doesn't work. You might have found last year's exercise, but I hope to check this maybe even now today. There are some things that have changed, so I want to check that the tests that we have work properly before opening the GitHub Classroom for everybody. But if you want and know how to, you can start working based on this template repository and then upload your files to your personal repository once it is available. But very shortly, exercise 6, you have list of origins, list of destinations. So it's kind of, well, again, there is a bit of gap still between the lesson and then solving this exercise on how to then do the routing between multiple origins and destinations. But it's quite a nice exercise. In the first point, you'll explore the data a bit, get oriented on the map, and then in the second problem, you will actually do routing and between all origins and all destinations. So kind of generating this origin destination information and then produce some statistics out of those calculations to verify your results. So that's it for today. So I will meet most of you hopefully next week, hoping to keep it quite relaxed. So I will introduce the final assignment in detail. If you are eager, you can already check the assignment from the web pages. Also, I have added 2 extra topics. So this QGIS materials were already in there if you want to self-study those. And then there is this quite a huge section related to raster data processing. And quick disclaimer about that, all the input data might not be available, but I have now posted all the materials there for you to check in case you want, for example, to explore these in your final assignment. But the raster materials are outside the scope of the course this year in Helsinki. Hopefully some year we will actually have a lesson and lecture on that. But as we are mostly using the methods and approaches covered in lessons 1 through 6 in our research as well, so that's what we are basing the lessons also on. Yeah, so thank you so much for sticking around. All the materials will be online. And finally, well, to advertise, I hope we get going with finalizing the book based on GeoPython and AutoGIS courses. So if you have any feedback on the lesson materials, feel free to suggest edits on the web pages or even contact us directly. So we are constantly developing the materials, and it's an iterative process. So we have tons of ideas and always then implement as many things as we can when developing the course. So that's wrapping up for the lessons, but now for the students who are still online, I'm happy to stay here and answer any questions about today's lesson or the course in general. But I will now pause the recording and say bye to all who were watching the lesson video.